In a previous video, we started exploring complex numbers, we learned about imaginary numbers, and we reminded ourselves a little bit about circular functions. Okay, now we're gonna use some of what we've learned to connect all the pieces together. So actually what we're going to talk about today are Euler's relations. But in order to be able to do anything with what we've got, we need to use Maclaurin series. We've dealt with Maclaurin and Taylor series in Introduction to Economic Analysis. So I would advise you to refresh your memory a little bit. I'm putting the links in the description of the video. Also, please remember that this is exactly the same series we used to expand E in our class on dynamic economic analysis. And actually, we're going to do this today as well. Let me just give you a main idea behind the Maclaurin series. Here, in case of this series, we are doing expansion around 0, and the idea is that we can transform any function into the expansion, into the polynomial function, where coefficients are given over here, and as you see, we have increasing powers of x. Here is like x to the power of 0, right? And we've got x to the power of 1, 2, until n. And of course, the more elements in the series we have, the better approximation of the function we've got. And we were denoting this part as polynomial n, right? Pn. Because n is the degree of the polynomial. Here, what we see is expression with n plus 1 out of some p, not necessarily 0 like in Maclaurin series. This is Lagrange reminder. Look, why do we need this Lagrange reminder? This is what we've got left, right? So, if it turns out, okay, so let's remind that this is Lagrange reminder. This part, and if it happens to be that limit with n approaching infinity out of R of n is equal to 0, this implies that limit with n approaching infinity out of Pn is equal f of x. Okay, what does it mean? Generally, we get that if n is getting bigger and bigger and it goes to infinity, and if in this situation Lagrange reminder goes to 0, we can say that this polynomial with infinite number of expressions will be a perfect representation of this function. This is why this reminder is so important, because if we can prove that it dies down to 0, then we can actually find a perfect representation of the function. Okay, and this is actually all we need, because now we're going to be expanding sine and cosine function. I just want to remind you from the last video that if I differentiate sine theta, I'm getting cosine theta. And if I differentiate cosine theta, I'm going to get negative sine theta. Okay, so what does this imply to us? Okay, So, first, let's consider expansion of the sine function. As you see over here, we need to have derivatives of the function for the expansion. So let's start by differentiating our function, which is sine, right? Let's denote this function as phi of theta, and let's see. Phi of theta is simply sine theta, right? But this implies, right, in this case, we need to also calculate value of the function, right, at 0. And phi of 0, which is equal sine 0, is equal to 0. Now look, what we need to do in the next step is to differentiate sine. If I differentiate this function for the first time, what I'm going to get is cosine theta, right? But in this case, we get that phi prime of 0 is cosine of 0, which is equal to 1. Then, if I differentiate it again, I got second derivative, which is equal to negative sine theta, and this implies that the phi b of 0 is equal to negative sine of 0, which is again 0. Then, if I'm gonna find the third derivative, it turns out that this is gonna be, right? Sine turns into cosine, so we've got negative cosine theta. So, this turns out, if I substitute 0 in here, in negative cosine 0, I will get that this is negative 1. Because cosine 0 is 1, we've got minus in front, it's negative 1. Okay, so now if I calculate fourth derivative of cosine is negative sine, minus up front, so we go back to sine theta, which implies that over here we'll have sine of 0, which is equal to 0. If I'm going to calculate fifth derivative, it's going to be equal to cosine theta. So, if I'm going to put 0 in this, I'm going to get that this is 1. And look, this goes on like that until nth derivative, with n approaching infinity. Now look, the funny thing that is happening is that after 1, 2, 3 differentiations, we are back where we started, right? Because we started with sine, and after 1, 2, 3, fourth, actually after fourth differentiation, or upon fourth differentiation, we are back to sine. And look, this means that every 4 differentiations, this pattern is going to repeat, because then we're going to have cosine, negative cosine, and sine again. So, knowing the first 4 derivatives actually allows us to conclude what are going to be the values of next derivatives. Because as those functions are cyclical, we can say that the pattern of derivatives here is also cyclical. Okay, this actually makes our job with Maclaurin series expansion a little easier. Okay, so we need to expand sine theta. So what will be the first? F of 0 divided by 0 factorial. I remind you 0 factorial is 1. So 0 divided by 1 is 0. Then we've got plus. Then we've got plus f prime of 0, which is 1, divided by 1 times x, but our x is theta. So we've got just plus theta. Okay, again, here we need to have 0 because second derivative here evaluated at 0 is equal to 0. And then plus. We will have third derivative, right? Third derivative is negative cosine, right? Cosine theta, which is equal to -1 when evaluated at 0. So here we need to change plus into minus, and we will have now theta to the power of 3, right? It would be like next element, not included here, divided by 3 factorial. Okay, what would happen next? Well, next we would expect, of course, to go back to sine, right? So again, this element will be equal to just 0. But then we would go to the fifth element in the series. This time, because here it's positive, we see that it's gonna be with plus. So now we've got 1 times, so we've got 1 divided by 5 factorial, and of course we've got theta to the power of 5. Okay, and I hope you can see that this pattern continues, and at the end, we're gonna have Lagrange remainder. Okay, so let's know that it's v n plus 1 out of some p times theta to the power n plus 1 divided by n plus 1 factorial. Okay, so now the question is, what happens with the limit with n approaching infinity out of this Lagrange remainder? Well, first, let's consider this expression. Look, this can be either sine, cosine, negative sine, negative cosine, right? So, this expression is always between -1 and 1. Now, here, we've got some number that is taken to the power n plus 1. So this makes this expression bigger, and this n plus 1 factorial is dividing this expression, so it makes it smaller. So you know we've got two conflicting forces. This part makes this expression bigger as n approaches infinity, and this part makes it smaller. Okay, so the question is, which of these two forces is winning? Well, without getting into detailed proof, you can imagine that this force is winning, because look, doesn't matter. Look, imagine that theta is 5, right? So here we've got a case of 5 times 5 times 5 times 5. Over here, we've got n plus 1 factorial. So here we have expression as 1, 2, 3, 4, 5, 6, 7. So at some point, at the beginning, this tendency will win, right? It's going to be stronger, but as n approaches infinity, we'll see that here we will have bigger and bigger number, here we will have the same. And actually, doesn't matter how big theta is, at some point, as n approaches infinity, this pattern is taking over, and this is how we can be sure, that this limit is equal to 0. So again, look, because here we have the same number repeated many times, and here we are actually getting bigger and bigger and bigger and bigger and bigger number, by which we multiply, which with n getting bigger by 1, by 1, by 1, by 1, we see that at some point this must dominate the expression, and it all goes to 0. And look, this means that actually we can get perfect representation of the sine function using Maclaurin series. So let me put this on the blackboard, because this is something that we are going to need very much in the future. Okay, I don't think we need this anymore. So, sine theta can be written as theta plus, okay, let me just, plus, minus theta to the power of 3 over 3 factorial plus theta to the power of 5 over 5 factorial. But look, knowing this, we can easily predict what's going to be next. Next, we will have minus theta to the power of 7 divided by 7 factorial. Then we would have plus theta to the power of 9 over 9 factorial. Then we would have negative theta to the power of 11 over 11 factorial, right? You see the pattern? And plus theta to the power of 13 over 13 factorial minus, and so on and so on and so on. Okay, so now that we've done this for sine, we need to do the same thing for cosine. But now that we know the trick to all of it, I think it should be very easy to do. Okay, just please give me a second to erase the blackboard. And let's start again. Okay, so now let's use a different notation. So we will have psi out of theta, and let's just say it's, well, we now need to expand cosine function, so we're gonna use, it's gonna be equal to cosine theta. And in these circumstances, psi of 0, which is equal to cosine of 0, is equal to 1. Okay, so let's move on. Then we've got psi prime, which is equal to negative sine theta, which means that psi prime of 0 is equal to negative sine of 0, which is 0. Then we've got psi b's equal to negative cosine theta. So psi b's of 0 is equal to negative cosine of 0, which is equal to negative 1. Then we've got psi third derivative of psi, which is going to be equal to just sine, right? Because of cosine is negative sine, minus gives sine. And this means that the third derivative evaluated at 0 is equal to sine 0, which is 0. Then we've got that psi, fourth derivative of psi, is going to be equal to cosine theta, which means that the fourth derivative evaluated at 0 is equal to cosine 0, it's equal to 1. And then we go to the fifth derivative, which is equal to negative sine theta, which implies that the fifth derivative evaluated at 0 is equal to negative sine 0, which is equal to 0. And we go. And look, what have we found? The same situation as with the sine function. So the pattern of derivatives repeats after every fourth differentiation. We go cosine, negative cosine, sine, cosine. So again, we can use this when we're gonna do the expansion using Maclaurin series. Okay, so what do we do next? Well, we use the formula to expand cosine. So first, derivative evaluated at 0, which is 1. I'm sorry, the function evaluated at 0, which is 1, divided by factorial 0, which is also 1. We start with just 1. Then, the next expression is going to be 0, so we can move to the third expression. And here we have second derivative evaluated at 0 is negative 1. So here we have plus. Okay, let's maybe write this all. We've got plus 0, and now minus. We're gonna have minus 1. So theta squared over 2 factorial. Okay, then we've got 0 again. We've got 0 again. And because here third derivative evaluated at 0 is 0. And then we move to the fifth expression. And here, with the fifth expression, we go back to cosine, right? We go back to what we already had. So, this is going to be 1 divided by 4 factorial times theta to the power of 4. Okay, then the next expression again would be 0. But let's don't worry about this. Let's worry about, of course, the remainder. However, look, here again, using the same reasoning, using exactly the same reasoning as we did in case of sine function, this expression can be either sine or cosine or negative sine, negative cosine. So it's always between negative 1 and 1. We know that this declining this expression force is stronger than the one that is increasing it. So we know that this is 0. And again, what we can do is that we can write this expression, we can write cosine function using Maclaurin series, and this is going to be a perfect representation. Of course, we are assuming that this series is infinite. Okay, so we've got cosine. We've got cosine theta. And this is equal to, first, 1. Then we get minus theta squared over 2 factorial. Then we have plus theta to the power of 4 over 4 factorial. And can we guess what's going to be next? Well, this is pretty easy. It's going to be theta to the power of minus theta to the power of 6 over 6 factorial plus theta to the power of 8 over 8 factorial minus theta to the power of 10 over 10 factorial plus theta to the power of 12 over 12 factorial minus and so forth. Okay, before we move on, I just want to point to you one thing. What would happen if we would combine those? Look, we would have 1, which is theta to the power of 0, divided by 0 factorial. We would have theta to the power of 1 divided by 1 factorial, and then we would have those expressions from both coming together. Because look, here we just got expressions with even powers, assuming that 0 can be treated plus 0, okay? And here we just have uneven powers. Is it going to be useful in the future? Well, probably, as this will be coming together. Okay, so now let's do something we already did in dynamic economic analysis. So let's just do Maclaurin expansion for e to the power of x. Now, so we are assuming that rho of x is equal to e to the power of x. We of course remember that e to the power of 0 is 1. So evaluating at 0 is becoming a pretty easy task to do. Okay, and what do we do? What about the derivatives? Well, we remember that actually derivative of e power of to power of x is the same as the function. So all the derivatives here, doesn't matter how many times we differentiate, are all the same and they are all equal to e to the power of x, which makes our job here extremely easy. Okay, so let's expand e to the power of x using the formula. So first we have e to the power of x, e to the power of 0, which is 1 divided by 0 factorial, which is 1, so we've got it. Then we've got first derivative, again, e to the power of x, which e to the power of 0, which is 1, divided by 1 is 1, but this time plus x. Okay, so I hope you can see that on the top, we will always have 1, right? So, not a problem. So, what will we have here? Well, in each consecutive element, we should have bigger x, x to the bigger power, so there's going to be 2, and divided by a bigger factorial. So, and we go on like this until we get to the remainder. And here we've got x to the power n plus 1. Okay, now let's evaluate this limit. Look, out of this, we will always get e to the power of p. Right? Doesn't matter how many times we differentiate, this is e to the power of x. If we substitute p, it's some number. So this is a constant. And look, again, we know the rule on those two. Right? So as at some point, because here we are multiplying n plus 1 times the same number, at some point, multiplying n plus 1 times, but we're getting a bigger and bigger and bigger and bigger number, is going to take over. So this is going to 0. So look, this is how we get third expression over here, and this is expression for e to the power of x. We know that perfect representation in time in terms of Maclaurin series, infinite Maclaurin series, is going to be simply 1 plus x square over 2 factorial plus x cubed over 3 factorial plus x to the power 4 over 4 factorial plus x to the power 5 over 5 factorial, and so on. Okay, these three results are going to be of extreme importance to us in our next step. I don't want to make this video too long, so let's just stop at this moment, and in the next video we're gonna start from this, and we're gonna begin going back closer and closer to differential equations and the solution in case of the complex root. Thank you for your attention, and see you in the next video in a couple of